Good evening, everyone. So today we are going to study uniform continuity. Okay. So welcome to my YouTube channel. Okay. So today we will study uniform continuity. So we start it. Okay. Uniform continuity. So this is lecture number 1. Okay. On this topic. So what is uniform continuity? So let I subset of R. I is interval. Okay. Okay. And F I to R real set of real numbers be a function, then F is said to be uniformly continuous on I if given any epsilon greater than 0. We can find delta greater than 0 such that fx minus fy, the difference of fx minus fy is less than epsilon whenever xy belongs to I with their difference is less than delta. Okay. So when a function is said to be uniformly continuous, if given any epsilon greater than 0, the difference of image fx minus fy is less than epsilon whenever x and y belongs to I with difference of x minus y is less than delta. Okay. So what is the speciality in uniform continuity? Okay. So we know that uniform continuity is defined on an interval. It is not defined on a single point. Okay. So uniform continuity is the uniform continuity have characteristic that it is defined on a interval, not at a single point. Okay. So remark, every uniformly continuous function f I to R is continuous on I. So why it is true? Because let you take a point. I want to show that f is continuous on I. So I will pick up a single point. Okay. And take epsilon greater than 0. Okay. Since f is uniformly continuous function, on I, we get delta greater than 0 such that fx minus fy absolute value is less than epsilon for all x y belongs to I with x minus y absolute value less than delta. Okay. So now take y is equal to x naught. Then we have fx minus fx naught less than epsilon for all x with x minus x naught less than delta. So what does it mean? It means f is continuous on x naught. Hence f is continuous on I. Since x naught is an arbitrary point of interval, so you can take any point and you can prove similarly as you have done for x naught. Okay. Okay. So every uniformly continuous function on an interval is also a continuous function. Okay. So we see some example of uniformly continuous function. What are those examples? Example 1m. fx is equal to x is uniformly continuous function on R. Why? Let's see its proof. So let epsilon greater than 0, then take delta is equal to epsilon, that is also greater than 0. Then obviously x minus y is less than epsilon whenever you are taking x y belongs to R with x minus y less than delta. Because delta and epsilon both are same, so this is automatically true. So this implies fx is equal to x is uniformly continuous function on R. Okay. So fx is equal to x is a uniformly continuous function. Okay. Okay. So we prove a result. Let f I to R be a function such that fx minus fy is less than equal to k times x minus y for some k greater than 0 and for all x y belongs to I. Okay. Then f is uniformly continuous on I. Okay. So let's see its proof. So it is given that fx minus fy is less than a times x minus y for all x and y belongs to I. Okay. So such functions. So the function who satisfies this condition called Lipschitz function. Lipschitz function. The functions satisfying this condition fx minus fy is less than equal to k times x minus y. Such functions are called Lipschitz functions. Okay. So Lipschitz functions, actually what we are going to prove? We are going to prove that every Lipschitz functions on interval is uniformly continuous. So what we will do? Let epsilon greater than 0. So we want to make fx minus fy less than epsilon, but we know that this is less than k times f minus y. If we can make this quantity less than epsilon, automatically fx minus fy will be less than epsilon. So we are going to solve for x minus y absolute value. So what we should take delta is equal to then for x y belongs to I such that x minus y less than delta, we have fx minus fy less than k times x minus y, but we are taking this less than delta, so it will be k times delta. But what is the value of delta? So what does it mean? For all x y belongs to I such that x minus y less than delta. So it means f is uniformly continuous on I. So every Lipschitz function is uniformly continuous on I. So the function which satisfies this condition fx minus fy less than k times x minus y, such functions are Lipschitz functions, and we have proved that in this theorem Lipschitz functions are uniformly continuous. Okay. Now we are going to see another example. Okay. Now example here. So what is that? So fx is equal to mod x is uniformly continuous function on R. Why? If we can show that this function is a Lipschitz function, then we are done, because every Lipschitz function is uniformly continuous. So what we know, let x y belongs to R, then we know that mod x, I can write this, I can add and subtract like that. Then by triangle inequality I can write like that. Okay. So this implies you take absolute value y left hand side, then what you will get? You will get this. So this implies this equation number 1, this is okay. Now interchanging interchanging x by y and y by x in 1, we get y minus absolute x is less than y minus x. But we know that y minus x and x minus y absolute value same. So this is nothing but okay. Further, I can take minus common. So this is okay. So from 1 and 2 we can write combinedly. Write 1 and 2 combinedly. We get plus minus absolute x minus absolute y less than equal to x minus y. Okay. So we know one result. Suppose we have two real numbers a and b belongs to R. Okay. Such that plus minus a is less than b, then we know that absolute value of a is less than b. Same thing is happening here. So what does it mean? Absolute x minus absolute y less than x minus y. But this is my f. So what is this? Fx minus fy is less than. So I can take k is equal to 1 here. So this implies this function is f is a Lipschitz function. But in previous theorem, I have proved that every Lipschitz function is a continuous, uniformly continuous function. So therefore, hence, fx is equal to mod x is a uniformly continuous function on R. Okay. On R. So we have proved that the function fx is equal to mod x. It means mod x function is uniformly continuous. Okay. Now, note that in lecture 2 we have already proved that sin x, cos x, cos sin square x, cos square x, all are Lipschitz functions. Because we know that f sin x minus sin y is less than x minus y absolute value. Similarly, we know that cos x minus cos y is less than x minus y. Okay. Sin square x minus sin square y is less than a times x minus y absolute value. Okay. Cos square x minus cos square y is less than x minus. These things I have told you when I taught you mean value theorem. Okay. In second and in mean value theorem lecture, I have told you about this. So sin x, cos x, sin square x, cos square x, these functions are Lipschitz functions. Okay. Therefore, hence, sin x, cos x, sin square x, and cos square y all are uniformly continuous functions on R. So we are going to prove some result, another result, important result. Let f I to R be a function such that derivative function is bounded. Derivative function is bounded. It means derivative of f at any point is less than equal to k for some k greater than 0 and for all x belongs to I, then f is a Lipschitz function and hence f is uniformly continuous on I. Okay. So let's prove it. Okay. Let's prove it. So one thing is missing. PA, sorry. No, it is okay. Okay. It is okay. So we know that derivative exists. F dash exists. And derivative of f is bounded for all x belongs to I. So if we take any 2 points, let x and y belongs to I, then by mean value theorem, we have already proved this result. Fx minus fy upon x minus y, derivative of f for some z in between x and y. Okay. So we can write this by this. You multiply both the side by x minus y. Okay. Now take absolute value both the sides. But this is bounded by k. So what does it mean? It means fx minus fy less than k times x minus y. So what is the meaning of this? What is the meaning of this? So meaning of this is this implies for all x y belongs to I. So this implies f is Lipschitz function on I. We know that every Lipschitz function is uniformly continuous, so this implies f is uniformly continuous on I. Okay. Hence we are done. Okay. So this was lecture 1 on uniform continuity. Next part of this topic we'll see in next video. Okay. So thank you very much for this lecture. Okay. So we will see you in next class. Kindly comment on this video, share, like and subscribe it. Thank you very much.